In this video, we're going to be talking about power series and the radius and interval of convergence. Okay, so a power series is when we have some summation formula and we write some sort of polynomial, okay, and versus a polynomial that's centered at C. And we kind of talked about that when we talked about our Taylor and Maclaurin polynomials. Okay, remember Maclaurin was centered at 0, which in this case would be here. Here it's centered at C. Okay, so it's basically we're writing a summation now as some sort of polynomial. And remember, that was kind of our goal throughout this entire chapter. So here, state where each polynomial is centered. So what you want to look at is you want to look at this term, this x to the nth term, okay? And you write that as x minus 0 to the nth. So my center is 0. Now we have this x plus 3 to the nth. And you always want to write this as x minus your c. So this turns into x minus a negative 3 to the n. So our center, apparently I made it fancy and added another e to the end, is negative 3. In the last example, I just had to stop the video. There was a mistake in here, and I had to look at the example. That was originally a 2. Go back and look at it. And I was like, wait, that doesn't make sense. X minus 2 to the n, okay, that's already in our form, so our center here is 2. Okay, so it's figuring out where the power series is centered. Notice how each one of them had to do with this term, where we have x to something to the nth power. Okay, so a power series can be viewed as a function of f of x, okay, where the domain of f is set for all x for which the power series converges, for which the polynomial approximates this series, and basically they like lie right on top of each other. Okay, so you can converge at a single point, on an interval, or across all x's. And if you think about, we've already talked about interval of convergence for some of our polynomials. Some of them were all real numbers. Some of them were over, a lot of them were negative 1 to 1. Okay, so convergence of a power series. Power series centered at C, precisely one of the following is true. Converges at a point, converges over an interval where you have a radius, or you can converge absolutely for all x. And the R is called the radius of convergence of our power series. Okay. The set of all values x for which the power series converges is called the interval of convergence. And we've kind of already talked a little bit about that in our examples the other day. So let's find the radius of convergence for this. And to find the radius of convergence, we use the ratio test. So we find the limit as n goes to infinity of the n plus 1 to the n plus 1 times by x plus 1 to the n plus 1 and then we simplify. Now I can't simplify. I was hoping I could simplify these, but those stay the same. And then this would simplify to just x plus 1. So typically you're going to have some piece involving n and then some piece involving x. Okay, and technically since I'm not taking the limit as x goes to anything, that x can come out in front. Looking at this, that's going to go to infinity. So this whole limit, this whole quantity equals infinity. So therefore we know that this diverges. I spelled diverges wrong, I apologize. Okay, but we have to check the center. Our center is 0. Actually, no, I apologize. The center is -1. So if I plug in -1 there, we basically get the series of, actually no, if I plugged in n equals 0, I would get a 1 plus, and then I would continue having stuff to the 0 power. I'm sorry, I would continue having 0 to a power, which would be, the rest of them would be 0. So in this case, our radius is 0. Okay, so a lot of times, I would say most of the time when you get an infinite limit, you check your center, and a lot of times that radius is going to be 0. Okay, so it's just convergent at that point. So it's just convergent at x equals -1. Okay, another example. So again, we do the limit as n goes to infinity of 5 to the n plus 1 times by x to the n plus 1 all over 5 to the n times by x to the n. Okay, and that simplifies to 5x. So in order for this to converge, the absolute value of 5x has to be less than 1. Stating this another way, -1 has to be less than x, has to be less than 1, has to be less than 5x. So if I divide by 5, looking at this a different way, that's my center, okay? And then on either side is my radius. So my radius in this case is 1/5. I could solve this inequality by dividing by 5. And then I'm going to get my radius. Okay, another example. Again, continuing through using the ratio test. Okay, so I use my ratio test, and this simplifies to this. Let me make sure I have my math right here. Yes, the 3's end up canceling. I have 1 to the 3rd over n plus 1. So this ends up being I guess I should technically still have absolute value signs over that. I just have bad notation. So when I simplify this, I get 0 for my whole limit. Okay? Since when you get a value of 0 for your limit, that means it is the radius of convergence is infinity. Okay, it's convergent for all x. So no matter what x I plug in here, I'm going to get, I'm going to be able to find the sum. Okay, next. So a power series whose radius of convergence is a finite number r, we have theorem 8.20 says nothing about the convergence of the endpoints. So we need to look at the endpoints now. Okay. As a result, so that theorem was the theorem that we talked about. I talked about it at the very beginning, I believe, if I can guess my screen correctly. It was either this one. No, it was this one. Okay. You can have a radius of 0, a radius of infinity, okay? Or you can have something in between. So basically, moral of the story, not really moral of the story. Basically, the idea behind this is you have to check the endpoints. And we'll go through a few examples where I go through checking the endpoints. And I'll show you what that all means. And this is very typical of a problem that you'd see on a typical AP year. So here we have the limit as n goes to infinity of my x to the n plus 2 over 4n plus 1 times by 4 to the n over x to the n plus 1. So now I get my limit. So this becomes 1, so my actual limit is equal to the absolute value of x. Remember, to be convergent, we need the absolute value of x to be less than 1, which basically means we need to be somewhere in between -1 and 1. Okay, so now you need to check the endpoints, okay? And I want to see this very clear. Show me x equals -1. So when I plug in -1, this is the series I get. Okay, so now you have to think about all those convergence tests we did and figure out, oh, when does this converge? Okay, or does this converge? Well, I see a -1, so I'm going to go straight to alternating series test. Sum as n goes to infinity of 1 over 4 to the n. Well, that equals 0. And we know that if I were to plug in a plus 1, this is definitely less than 1 over 4 to the n. Okay, so this converges by the alternating series test. So you would include -1 in your answer. Now if I check x equals 1, if I check the other endpoint. So now I plug in 1 for x, which then this simplifies to, I don't know why I just rewrote the same thing. 1 to any power is that. We know that this diverges because it's a harmonic series. Or we could say diverges by the p-series test because p is equal to 1. So our interval of convergence in this case is -1 to 1. Our book writes it in interval notation. I don't know why I write it as an inequality. Okay, I do have a couple more examples planned here. So I have these two examples. I'm not going to actually do those. I'm going to teach those to you guys during class. And let's move on to a different theorem or concept, because if I teach you this video is going to be 30 minutes long. Okay, so properties of functions defined by a power series. So say I have a power series here, and I have a certain radius of convergence. If you're differentiable, and we can take the antiderivative, the radius of those series, by either differentiating or integrating, is the same as the original power series. But the interval of convergence may change depending on the behavior at the endpoints. So again, you still want to check the endpoints. So let's do an example having to do with that. Okay, so we consider this function, find the interval of convergence for each of the following. Okay, so for my f of x function, so I'm going to find the interval of convergence. Actually, before I do that, I'm going to actually find what this series is. Okay, so this series is so now if I were to take the derivative of that series, because we're going to need that here in a minute, if I were to take the derivative of this term is 1, derivative of this term is 4, x minus 2 plus 9 times x minus 3. Now, of the general term, so if I were to take the derivative of this general term, I would get n squared x minus 2. This should be a 2. This should be a 2. I think I was worried about the 3. To the n minus 1. We're going to need that, so that's why I did that. Okay, now if I integrate f of x with respect to x, okay, remember we would have some constant c in there, but if I were to integrate this, if I were to integrate this function, I would have 1/2 x minus 2 squared plus 2/3 x minus 2 to the third plus 3/4 x minus 2 to the fourth, and so on. And so my general term here is going to be n times x minus 2 raise your power to 1 over your new exponent. Okay, so we're going to need that. Okay, let's use this original to find the interval of convergence, because they tell us the interval is going to stay the same. We just need to check the endpoints. So the limit as n goes to infinity of the absolute value of n plus 1 times x minus 2 to the n plus 1 all over n times x plus 2 to the nth. This simplifies to be n plus 1 over n times the quantity x minus 2. Okay, taking that whole limit equals x minus 2. Remember, for that limit to converge by our ratio test, if we want this to converge, this has to be less than 1. So therefore, -1 less than x minus 2 less than 1. If I add 2, we get this to be our interval of convergence. Okay, so now what we need to do is we need to check the endpoints. And we need to go through and we need to check the endpoints for each one of the functions. So again, I'm still working with f of x. If I check the endpoints for, if I plug in 1, this diverges by the nth term test. Because as I go to infinity, that this would not equal 0. Okay. Now I'm going to check. I checked 3. Now I'm going to check 1. Actually, no, I checked 1. 3 minus 2. Well, that's 1 to the. So this still diverges. Okay. So for the original function, this is my interval of convergence. 1 to 3. Okay. Now I continue doing that. I'm going to do that for. I'm going to erase some of this stuff because I'm running out of space. I apologize, you get to see me erase. Isn't this a fun video? Seeing the teacher erase. It's all very exciting. Look, she missed a little bit. I wish it was like a smartboard. I'm using PowerPoint. I wish this was like a smartboard where I could just do like a big circle and erase everything. Okay, so now let's worry about the integral of f of x dx. Okay, so now you could do the ratio test and get this same interval back. It was funny. I was doing this last night in preparation and recording of today. I did the ratio test and I got the same interval and I was like, well, wait, if you go back, it says the radius of convergence, the interval of convergence is going to be the same. Okay. But you have to check the endpoints. So, okay. So now I check my endpoints. Remember, we're using this. So basically we have this series. Where we're checking the endpoints, we're checking the endpoint of x equals 1. So if I check x equals 1, or basically if I'm plugging in 1 for x, I get n over n plus 1 times by negative 1 to the n plus 1. Now this diverges again because the limit as n goes to infinity of n over n plus 1 by the nth term test. Okay, so now I check x equals 3. So when I plug in 3 for my x, I get this, which we know also diverges by the nth term test. Okay, lastly, so again, my interval of convergence, there is that. So then for my derivative, okay, again, it's the same interval, it's 1 to 3. So I check x equals 1 in my derivative. So my derivative formula is this. If I plug in 1, okay, this diverges again by the nth term test because the limit as n goes to infinity of n squared is equal to infinity. Okay, and then we test x equals 3. n equals 1. I'm sorry, I'm trying to go through this really fast. 1 to the n minus 1, again, diverges by the nth term test. Now, if you look in the book has an example where they're not all the same, where one of the endpoints actually works. So you're welcome to read the book and go through that example if you want. I apologize for the super long video. Realize it would have been a lot longer if I would have done those additional examples. All right. Thank you for watching our power series, and really it's interval of convergence.